So review. What we saw is, so if we have quadratic forms, Q1 and Q2 are equivalent, if there exists some gamma in, well, you could be more general than this, but let's say SL2Z, two quadratic forms are equivalent, if there's an element of SL2Z so that one is composition with the other. And we had formulas for what, if this is the form A1, B1, C1, then this form A2, B2, C2, we had explicit formulas for how that change happens in terms of ABCD of gamma, little a, b, c, d. We proved that they have the same discriminant. D, b squared minus 4ac is the same for 1 as 2. And we saw that the roots alpha of Q1, negative b1 plus root d. So let's consider the case, I keep saying consider first this case, but we've run out of time, so this is the only case we'll consider is the negative discriminants, that is the definite forms. So the discriminant is negative, so this d is an imaginary number, and I'm taking the plus sign, so this is over 2a1. This is in the upper half plane. That's the set of complex numbers with imaginary part positive. We've just split the complex plane into two. And we learned that the action of gamma of SL2Z on quadratic forms mimics that. We showed that the quadratic form Q2 has root which is equal to gamma inverse acting on the first quadratic form's root, where this action is by fractional linear transformations. Fractional linear transformations. In other words, a matrix ABCD takes a number z in the upper half plane to AZ plus B over CZ plus D. Okay, so far so good. All of this is review, and we're well accustomed, and it all makes sense. We know what's being said. Stop me if at any point I'm saying something that's not entirely clear, especially now that you've had some practice with it. Maybe there's some subtleties that you wanted clarified or something. So please stop me. Anybody? Okay. And then we learned a reduction algorithm. So reduction algorithm. In fact, there was nothing special about the starting points being points that come from quadratic forms for any z in H. So here's the upper half plane. No matter what z is, what we can do is we can use T or T inverse, that is the matrix 1, 1, 0, 1 or 1, negative 1, 0, 1, which has the effect of translating the real part by 1 to make real part between minus a half and a half. So here's negative 1, here's positive 1, here's minus a half, and here's positive a half. So we have this region. And then use S, which is 0, negative 1, 1, 0, to move outside the unit circle. So the complex unit circle, which we're only looking in the upper half plane, so I'll only draw the upper half of the complex unit circle. So you move z until it gets inside the minus a half, then you use this reflection, which is really a reflection and a flip over the y-axis, and then you move inside half, and then you do this, and eventually you find then there exists a z1, which is some transformation, which is a word in s's and t's, which is in this region. So let's call this region F. This is called a fundamental domain. Which is the set of points in the upper half plane. So it's already complex with imaginary part positive, with real part between minus a half, and imaginary part, or not imaginary part, but absolute value, not inside the unit circle. Okay, this is almost unique. If I wind up on the 1/2 line, I have to choose, do I want the minus 1/2 line or the plus 1/2 line to be the smallest? Doesn't matter which. Typically people make this choice, that this half line is the smallest. And then, so this bit of the boundary is not included in the domain. I don't really care for our purposes right now. And then there's a question of, you see what S does to the boundary here is that it interchanges this part of the boundary with that part of the boundary. So people will typically take this part of the boundary and not that. So those two pieces are equivalent under S. These two pieces are equivalent under T. And so just choose one, doesn't matter which one, and that's more then the fundamental region becomes unique. So there's a unique z1 for every z and a unique gamma. But it doesn't matter. All I'm saying is there is this reduction algorithm that will make z sort of in this region. Now there's one subtlety. So I didn't prove this theorem. So this is a reduction algorithm. I mean, this is a theorem, the reduction theorem. The theorem is that there exists such a thing. And a sketch of a proof is the following observation. So wherever you start, no matter how low you start, here's the region I'm trying to wind up in, minus a half, 1, minus 1. The imaginary part, when you do this operation, the proof says that 1 doesn't change the imaginary part. Doesn't change the imaginary part. You see, the real part I can always get between minus a half. That's easy. What's going on to the imaginary part? 2 increases it. This is the key. So wherever I start, I can move it into minus a half. When I apply 2, that's inversion through the unit circle. So the image has a larger, even though the image is really here, the image has a larger, so if this is whatever W, then this is SW. The image has a larger imaginary part. And so now, whatever that original imaginary part was, all of these orbits that we're getting, all of these points that we're getting when we use 1 and 2 repeatedly, are in this compact part of the fundamental of the upper half plane. So let me write that down. As we move z by s and t's, and t inverses, of course, if we need to apply s, it's because, let's call it z1, this image, some gamma 1 acting on z, is in The only time you apply S is when you're inside the unit circle, but you can't be inside the unit circle any more than wherever the imaginary part of Z started. Is in a region, the set of, gosh, I need a new letter now. The set of W in the upper half plane, so that the real part of W is less than a half in absolute value, because that's what T will do. I have to apply S, that means the absolute value of W is less than 1. But that entire region is not compact because the boundary, there's this boundary of the upper half plane, since the upper half plane's open. But the observation is that the imaginary part of W is at least, the imaginary part, which is positive, I don't need absolute values, it's at least the imaginary part of the starting value. If I start with Z, whatever Z was, then I wind up in this compact region. Okay? And what do you guys know about compact regions having infinitely many points? This is compact in the sense of being closed and bounded. Okay, so not everybody has had point set topology yet. But if you imagine, I have infinitely many dots, and there's only so far they can go, there's nowhere for them to go, they have to have a limit point. So if this process went on forever, we would get a limit point along a subsequence. We get a limit point along a limit point in this compact region, right? If we had infinitely many points, at least somewhere it has to bunch up. And that can't happen because the matrices we're using, A, B, C, D, are integral. And limits of integers do not have, this is a discrete action. So that's why I'm putting quotes around the word proof. There's some concepts here that would take us a little bit more time. But the matrices have integer entries, have A, B, C, D in the integers. So the action is discrete. I realize I haven't given you a formal definition of this, so there can't be limit points. So there. You can make all of this precise. I just, in the interest of time, I'm giving you the flavor of the ideas. So there can't be limit points. And if there can't be limit points, this process can't go on forever, and the process only halts when you wind up in the fundamental region. The process only halts when you wind up in this fundamental region. Okay? So the process halts. This moving into the minus a half and using inversion halts, and does so once you're in this fundamental region F. Okay. So any questions about that? We saw it in practice, but here's a sketch of a proof of why it will always happen. I claimed that when we did this, not for arbitrary complex numbers, but in particular for the ones that are roots of binary quadratic forms, we got a simpler quadratic form. So I want to make that process, I want to make that concept precise. Okay? So y is the resulting form, let's call it Q, with root in this fundamental region, simplest, or reduced. Let's just use the actual terminology, reduced. Okay, so this is what I want to argue for you. The two forms I gave you on your quiz, They weren't that much more reduced. It turned out that there was only one step to do, and it was the same step. Yukon? Right. I'm trying to make this notion precise. So let's see what simplicity means, what this reduction is, what makes it reduced. So let's look at the condition. Here's the condition. Alpha, which is negative b plus root d over 2a, is in F. What does that mean? That means, what does it mean to be in F? F is defined by the real part being less than a half. What's the real part of alpha? Thank you, Dependro. Exactly. D is imaginary, so the real part is right here. So the real part of alpha, also known as negative b over 2a, has to be less than a half. Ah. Okay. So, what have we learned? That means that I guess it's if and only if, absolute value of b is less than or equal to absolute value of a. Okay? Let's say the form is positive definite. So assume we know that Q is definite. Let's say Q is positive definite. So it takes, it could take either, definite means it only takes one sign. It only takes positive numbers or it only takes negative numbers. And that's a consequence of this discriminant being negative. So we already are looking at definite forms. The question is, are they positive definite or negative definite? If you remember, Q of 1, 0 is always A. And so if it's positive definite, then A automatically is positive. So I can drop this absolute value. Okay, so this implies absolute value of B is less than or equal to A. Okay? So that's one condition. So this isn't if and only if until I add the second condition. So the fact that alpha is in the fundamental domain means its real part is between minus a half. And if I cancel the 2's and I move the absolute value of a to that side, I get absolute value of b is less than or equal to absolute value of a. But we can assume, by restricting the positive definite cases, that a is in fact itself positive, in which case b is less than or equal to a. Okay? Now there's another condition. What's the other condition? The first condition is that the real part is between minus a half. The other condition is yes, exactly. The norm is bigger than 1. These are the two conditions. Real part is between minus a half, and the norm is bigger than 1. So the norm of alpha needs to be bigger than 1. I guess bigger than or equal to. I mean, I said equals. Good. Bigger than or equal to. I'm being a little sloppy with the boundary. And what is that? So what is the norm of this complex number? The norm of this complex number is the real part. So there's a 1 over 4a squared. I can square. Let's take the norm squared. Let's square both sides. So norm squared is bigger than 1. That's the same condition. There's this factor of 1 over 2a, which pulls out as a 1 over 4a squared. And then I get the real part squared plus the imaginary part squared. So the real part squared is b squared plus the imaginary part squared. And the imaginary part squared is square root of d, but it's the absolute value of square root of d, right? You know what I'm saying. This is, let me make this positive and then explicitly put the I so that you see it there. So then it becomes the absolute value when I take the square. Does everybody see that? Does everybody see how I got this condition? can you say I see or go back, please, in the chat? Just so I know if everyone's seeing what I'm doing. Yes, let's go over it one more time. Sriya, can I bother you? Can you unmute yourself so that I can go back a little bit?
Hello?
Yes. Hi, Sriya. So, are you happy with the? Are you happy with anything that I've said so far? How far back should I go? That's right, Yukong. That's where we're headed. Yes, Sriya. How about? Yeah, go ahead.
I guess from like the beginning, if that's okay.
Okay. So, are you happy with the fundamental region?
Yes.
Okay, so we have this fundamental region, which is this picture with minus a half in the real part, and norm outside of the unit circle. So norm at least one.
Okay.
Okay. So let's suppose, just like you did on your quiz, you took some alpha, and you moved it into the fundamental region. So you've reduced your quadratic form.
Okay.
Now I called it reduced, but let's really understand what that reduction means. So you've taken this alpha, which is negative b plus root d over 2a, and you've moved it into this fundamental region, this
Right.
fundamental domain. So that means that the real part of alpha is less than a half.
Okay, that makes sense.
And what is the real part of alpha? We just read it off of here, because this is the imaginary part. The real part is negative b over 2a.
Okay.
Okay, so that gave us one condition on being reduced.
Okay, and then the other condition comes from the norm of z must be greater than or equal to 1.
Yep. And the norm of z is the norm of alpha. Z is alpha in our case. So the norm being greater than 1 is the same as the norm squared being greater than 1. Okay? And now we have to work out what the norm squared of this thing is. Okay? Okay. Right. So we're trying to work out what the absolute value of this thing is. Complex absolute value squared. Right?
Yes.
So there's a 1 over 2a, which is just a factor floating around. So let's pull it all the way out with a square as a 1 over 4a.
Okay.
And then...
Oh, the initial confusion was where the b squared plus absolute value of d came from.
Okay.
So
Yeah, so then what's left is the real part, which is b, or negative b. But we're squaring it, so we don't need the minus sign. And then the imaginary part squared. And the imaginary part is square root of absolute value of d. I mean, d is negative, so absolute value of d is negative d.
Okay. I think I was confused because I was thinking, like, since we're squaring alpha, doesn't that mean that, like, we should be multiplying by the conjugate?
Yes. Yes. So if you multiply, so another way of seeing this, let's write it out as a multiplication by conjugate. So it's negative b plus root absolute value of di over 2a times the other alpha, the other root, which is negative b minus root absolute value of di over 2a. Exactly what you said.
Oh, okay, yeah. That makes more sense.
So there's the 4a squared that pulls out. And then here we get a difference of squares. So we get negative b squared, which is b squared. And then plus, minus I squared, which turns into a plus. And then root d squared, which is just the root absolute value of d squared, which is just absolute value of d.
Okay, I think I was multiplying it wrong in my head.
I see.
But it makes more sense now.
Okay, great. Thanks for helping me out. Okay, so now what? Yukong already told us what's about to happen. Let's just simplify this a little bit, because we have b squared. The absolute value of d is negative, so its absolute value is its negative. Right? Everybody see that? And then here we have a 1 over 4a squared, but remember what d is. It's b squared minus 4ac. Aha. So what happens here? Does everybody see? The b squareds will cancel, the minus signs will cancel, and the 4a will cancel. So all I'm left with is, want to take a second with the algebra and then type in when you see what the answer is? Why is it minus d? D, we're assuming throughout that d is negative. So to give us definite forms, so that the whole picture takes place in the upper half plane. There's something completely different. It's not completely different. It's extremely similar, but it starts looking completely different if you think about it geometrically and not p-adically or something. There's a different process if the discriminant is not negative. So I'm dealing with negative discriminants. I'm restricting Sheik to this discussion to negative discriminants. Okay? If anyone sees what this algebra simplifies to, can you write it into the chat, please? Right. You get negative. Let's see. The b squared and a minus b squared, they cancel. The minus and the minus also cancel, so I think I should be getting a plus sign. And then I have a 4a, so let's just say plus 4ac over 4a squared. The 4's and one of the a's cancel, and I just get, yep, c over a. Exactly. Exactly. Does everybody see that? So check out this condition. If you chase this all the way back, c over a has to be bigger than 1. Let me move a to the other side. A is less than c. And I know I'm not multiplying by a negative number when I do this, because a we assumed was positive. Does everybody see that? So these are the conditions. It's actually quite a simple set of conditions. What we've shown, so theorem, lemma, let's call this lemma. We're about to have a really deep theorem. Lemma, Q being ABC, is reduced in the sense of its root being in this fundamental domain if A is bounded by C and bounds absolute value of B. And if you look back at your reductions, you started with, what was it, 14.32 or something? And after reduction, that became 3.213? Is that what it was? What was it? Let's see. A is the middle one. B is the smallest. A is the middle one. C is the largest. Is that what most of you got for that problem on the quiz? Can you write in yes, that's what I got, or no, I didn't get that? Okay, good. Yes. Is Sheik the only one paying attention? Can I just? Oh, you didn't get You didn't get that, Stephanie. All right. Then you made some simple calculation error. But that's okay. So that's the point. So B might have to be negative, but its absolute value is no bigger than A, and then C is over here. Now, this lemma will allow us to prove the fundamental theorem, and this is what I want to end on, and then we'll start reviewing everything, but we'll kind of see everything out of this lemma. Out of this lemma, so does everyone see how we prove this lemma? Is anyone completely lost? Can you write in, I'm with you, or I'm lost? Great. Great. Dipendra, what do you mean the discriminants are not the same? Which discriminants are not the same? in the examples I just gave. That shouldn't be. 9 minus 4 times 2 times 14. What was it? I was trying to do it from memory. 4 minus 3 times 13. Anybody? Oh, 2, 1. That's what it was. 2, 1, 13. Thanks. 2, 1, 13. Thank you. Hopefully that's good now. Great. Great, great, great. Thanks, guys. Now are the discriminants the same? 1 squared minus... I mean, I can't do this operation in my head. You got scared. Yeah, it's... you were right, I was wrong. Okay, so do you see how this is what it means to be... We could make this the definition. We made our definition of a quadratic form being reduced, that its alpha is in the fundamental... you can't see what I'm pointing to. What we said was the form Q will be reduced if alpha is the smallest... If alpha is in this fundamental region. But now we have a lemma that connects this. It's in... The alpha will be in a fundamental region, if and only if we have this condition. And so now we can prove a fundamental theorem. If we remember, again, recall, two forms are equivalent implies the discriminant of the first form and the second form are equal. Daniel? This check for being reduced only applies to D negative. Well, there's a way to make this also work for D positive. But we haven't talked about it. Right. So what we've said so far is Q being positive definite. Q being positive definite, reduction is this. But actually the same process works for indefinite forms as it does for positive definite forms. And of course negative definite is the same thing with negative A's instead of positive A's. Okay? If you're trying to understand definite forms, just multiply Q by negative Q, and then if it only takes negative values, multiply it by minus sign and look at what positive values it takes, and you know everything about its negative values. So it's enough to consider either positive definite values or indefinite values. So I haven't explained to you, Daniel, why this same thing will apply and what reduction means in that case, but it will be the same lemma. Okay, so we remember that if two forms are equivalent, then their discriminants are the same. The converse need not be the case. Converse, not necessarily true. And here's how we can work that out. In fact, the failure of the converse being true or not, when the converse isn't true, that's exactly measuring a lack of unique factorization. So we're gonna come all the way full circle to unique factorization domains right now. Let's see two examples. So example 1. Example 1. This was the first form that we dealt with seriously, x squared plus y squared. What is its discriminant? B squared minus 4ac, all together now. B is 0. Yes. Everybody see that? The discriminant is negative 4. Okay? If you write down another quadratic form of discriminant negative 4, let's see what the reduced forms of discriminant negative 4 could possibly be. So negative 4, are there others? So, are there... And is this reduced? Is this form reduced? A is 1, B is 0, C is 1. the inequalities are satisfied, right? This form is reduced. By the way, what's its root? So let's call this Q. What's its root? Think about it for a second and then tell me your answer. Type it into the chat once you've figured out what the root is. Right, and we want the root, exactly. Everybody see that? This root is I. In fact, this quadratic form in this fundamental domain, negative a half, positive a half, 1, 1, 1, negative 1. This quadratic form, let's call this Q0. The sum of two squares is right here. That's I. That's the quadratic form. That's alpha of Q0. There's the sum of two squares. That's what I means. I in the upper half plane means the quadratic form, which is the sum of two squares. Z adjoin I. Okay? This is also the space of lattices. I don't have time to go into what this has to do with lattices, but you will see some hints of that right now. So are there other inequivalent forms of discriminant 4? Discriminant negative 4. So let's think about this. D is equal to b squared minus 4ac. And d is supposed to be negative 4. Okay? Well, I don't like that minus sign. Let's flip things around. That means 4ac minus b squared needs to be 4. You see that? Now, A and C, we're dealing with definite forms. A and C are positive. A and C are positive. This is 4ac. This is a positive number minus a square. So if A and C are the biggest, you see, they're both bigger than B. In particular, C is the biggest one. Dipendra, you see what I'm about to say? Okay, let's look at this form. 2, so you're saying the form 2, 2, 1 is also a form with discriminant 4? So let's call this Q1. What's the discriminant of Q1? It's b squared minus 4 times ac. So this is 4 minus 8 is negative 4. Yep, I agree. Is this reduced? No, because as you can see here, C needs to be the largest, and C is not the largest. So I claim that this form is actually equivalent to Q0. So my claim, without doing anything else, is that Q1 is equivalent to Q0, because in this case, for this discriminant, there's only one reduced form. That's my claim. Now let's see why that's true. A and C are the largest ones. So when I subtract off b squared, well, how am I supposed to get 4? How am I supposed to get 4? Well, let's move it to the other side. So let's think about this. I just want to think about positive numbers. So 4ac needs to be equal to 4 plus a square. Except that b needs to be less than, so let's make this side bigger. I'm going to make this side bigger by replacing b by a. Does everybody see that? Since if I have another reduced forms, are there other inequivalent forms of discriminant d? So if it's inequivalent, well, and I mean reduced. since any form can be made reduced, we may as well just look at the reduced forms. So the reduced forms are the ones that satisfy this inequality. C is less than or equal to A. C is greater than or equal to A is greater than or equal to the absolute value of B. Okay? So B is smaller than A, so that's an inequality, and C is bigger than A. So this is an inequality, 4A squared. Does everybody see that? And wait a second, what does that mean? This means, let's bring one of the A squareds to the other side. 3. So this is a 4A squared minus an A squared. That's a 3A squared is less than or equal to 4. In other words, A squared is less than 4/3. And that's an integer. So the only possible values of A are 0 or 1. Does everybody see that? Okay, let's look at these two cases separately. Okay, let's look at these two cases separately. If A equals 1, well, B could be either 0 or 1. It could be 0 or it could be 1 or it could be negative 1. I'm just looking at this equation. B is bounded by A. Does everybody see that? Have I lost anyone, or is everyone following along? This is all kind of completely elementary arithmetic, so it's on one hand trivial, on the other hand very easy to get lost if you don't see what I'm doing. So here I'm using the fact that absolute value of B is less than or equal to A. And if A is 1, then this is our only choice. There's another option, which is that if A is equal to 0, well then what do we know about B? B is bounded by A, and A is 0. So B is 0, and D is B squared minus 4AC, and if B is 0 and A is 0, then D is 0. So that's not possible, right? This we rule out. Does everybody see that? So A can't be 0, because D is not 0. We're trying to understand D equals negative 4. Now, let's look all the way back up here. What do we know about B? This will imply that B squared is 0 mod 4. If we look mod 4, we have a B squared is equal to 0 mod 4. In other words, B is even. So B is even. That kills off these two conditions. This is because B is even. B squared is 0 mod 4. So our only option is A is equal to 0, B is equal to 0, and then what is D? So D, which is negative 4, is equal to B squared minus 4AC. Now we just solve for C. B we said was 0, A we said was 1. So C is 1. So what have we proved? What's the form 1, 0, 1? That means that Q, the only reduced form is 1, 0, 1. But that's x squared plus y squared. So we just proved a lemma. If Q is a quadratic form and the discriminant of Q is negative 4, then Q is equivalent to 1, 0, 1. So all the forms of discriminant negative 4 are all equivalent to one another. Why? Well, whatever the form is, you can reduce it, and then we looked at what the reduced forms are, and there's only one. Does everybody see that? Does that make sense? Can you write lost or cool? Cool means it makes sense. Lost means something doesn't make sense. Can you write that into the chat so that I know who's with me? Cool. Only Alex? Everybody else is somewhere between lost and cool? Okay. Okay, great. Great. Let's do a few more examples of this. We'll start to get better and better at it. Okay, so here's another example. Example 2. What was our other quadratic form? Let's call this Q1. The norm form for the Eisenstein integers, right? X squared minus xy plus y squared. Is that what it was? This is the norm of x plus omega y. What's its alpha? What's its discriminant? -3. B squared is 1 minus 4ac. The discriminant is -3. Exactly. The discriminant is -3. And let's do the same computation and learn what the possible, are there other, so question, is it reduced, by the way? Is this reduced? So this is the form 1, -1, 1. Is it reduced? Does it satisfy this series of inequalities? Well, they're all 1 in absolute value, so, and 1 is allowed. Yes. So this is reduced. It's positive definite. It's definite because the discriminant is negative. It's positive because A is positive. Are there others? Are there other reduced forms equivalent, not equivalent to Q1? Are there other classes of forms? Remember, we took forms up to equivalence and that made a class of forms. By the way, what's this root? What's alpha Q1? Yes, you guys see that? Negative b plus or minus square root d over 2a, also known as r cubed root of unity, which, by the way, is right there. This is w, omega, and this is the Eisenstein integers, and that's the lattice generated by 1, and omega is z adjoin omega. Okay, I'm planting all kinds of seeds for the future. We don't have time to understand all of these things properly. But these are seeds for the future. More magic that's begging to be uncovered. So that's where this is alpha of Q1, where Q1 is the norm form of the Eisenstein integers. Okay, let's do this computation. Let's answer this question. So if ABC is reduced, that is, absolute value of B is less than absolute value, is less than A is less than C, and the discriminant, which is B squared minus 4AC, is equal to -3, what can we learn? What can we learn? First of all, what do we know about B? Is B even or odd? This is even, this is odd, B had better be odd. B is odd. Good, that'll spare us a little bit of time. Let's move this and this to the other side, just to make everything positive. This tells us that, I'll move the 4AC to one side. 4AC is equal to B squared plus 3. I moved 4AC to that side, I moved the 3 to the other side. And again, B squared is at most A squared, and C is at least A. So what have we learned? I'll subtract an a squared to this side, so 3a squared is at most 3. So a is at most 1. So we have two options. A is equal to 1, or a is equal to 0. Let's follow a equals 0. If a is 0, then b is bounded by a. If a is 0, then b is 0. And if a and b are both 0, then the discriminant is 0. So that can't be. In fact, that's a general fact, now I hope we see, that a can't be 0, because if a is 0, then b is 0, then the discriminant is 0. We're not looking at the 0 discriminant. Okay, so a is 1. So a is strictly positive in general. So a is 1. That gives us three options for b, which is b is plus 1, or b is 0, or b is minus 1. Can b be 0? Devendra says no, because b is odd. So b is odd, so b can't be 0. Okay, if we have plus 1, that means that the discriminant, negative 3, is b squared minus 4 times a times c. So c is equal to 1. Exactly. Thank you, Sriya. How about if b is negative 1? If b is negative 1, then we get 3 is equal to negative 1 squared minus 4 times a times c. Same equation, same thing. So c is 1. Oh, look, there are two quadratic forms. So we have two forms. Our options are q is this potential reduced form is 1, 1, 1, 1, 1, 1, or q is 1, negative 1, 1, 1, negative 1, 1. Ah, so the class number is not 1, and there's not unique factorization in the Eisenstein integers. Yes, yes, of course there's unique factorization in the Eisenstein integers. Yes, it's a PID, so what's wrong? Where's this root? So this is our original q. This is our original q. This root we already worked out is omega. What's this root? It's not the bottom half. It's not in the lower half plane. Daniel? Yes, exactly. So this was, hang on. Did we say this was omega? Uh-oh. I said the wrong thing. This isn't omega. This is plus 1/2. Ah, I got this a little backwards. This is plus 1/2. Darn it. I'll draw the fundamental domain again here. The plus 1/2 root is right there. This is omega plus 1. And this root, the 1, 1, 1, this is x squared plus xy plus y squared. This is the root that's actually omega, because it's negative 1 plus root 3i over 2. This is actual omega. This is omega plus 1. So this is the issue that I said with the boundary. The boundary, these 2 points are equivalent. They're equivalent under what map replaces w plus 1 with w? Or w with w plus 1. T, exactly. So these are equivalent. These are equivalent. But they're on the boundary. They're on the boundary of the fundamental region, the fundamental domain. Okay, so you have to be a little careful when you're on the boundary to decide whether things are equivalent when you get more than one quadratic form. Okay? So need to be careful with the boundary. But since we were careful with the boundary, we can prove a lemma. If Q is ABC and the discriminant is -3, then Q is equivalent to the norm form of the Eisenstein integers. Cool? Does everybody see that? Let's do one where it's not going to work out so well. Okay, so example 3 is the norm form, let's call this Q2. It's the norm form of the first place where we know that there's going to be some non-unique factorization. This is x squared plus 6y squared, which is also the norm of, 5. Which is the norm of x plus root minus 5y. Right? Because 6 factors, this is exactly the ring where 6 is 2 times 3, and it's also 1 plus root minus 5 and 1 minus root minus 5. And we're going to see these two different factorizations manifest themselves in terms of the fact that the class number here is not going to be, the discriminant here will have more than one representative, more than one reduced equivalence class. Okay, so what's the discriminant? Let's do this calculation a little bit more quickly maybe now that we're getting the hang of things. Yep, -20, b squared minus 4ac, b is 0, minus 4a is 1, 5 is, ac is 5, so this is -20. All right, so we got a pretty big discriminant to deal with. Let's try to get through it. What are our options? If Q is reduced, that means absolute value of B is less than or equal to absolute value of A is less than C. What do we learn? And we have this equality. So let's turn this equality. Let's move things around so it's positive. I'll move this to the other side, 4AC. I'll move the 20 to the other side, 20 plus B squared. If it's reduced, then I can replace B squared by A squared, 20 plus A squared. And I can replace C by A, and that makes this side smaller, 4A squared. And that means that 3A squared, when I subtract the A squared to the other side, is at most 20. Which means that A squared is at most 20 over 3, 6. Is that right? Is anyone following this? 20 thirds is about 18 thirds, and 18 thirds is 6. I mean, A is a whole number, so I don't need any fractions here. And a square being at most 6 means A is 1 or 2. A is not 0, as we saw already. So now we really have two things to think about. A could be 1, or A could be 2. If A is 1, now let's rule out a couple of things about B. What do we know about B? Even or odd? Even. This look mod 4, this is 0 mod 4, this is 0 mod 4, B is even. So that'll help narrow down some of the cases. So if A is equal to 1, the only thing B can be, B has to be even and less than A. So it's either -1, 0, or +1, but it's even, so B is 0. And C, when you do this computation, is 5. That's our original quadratic form. That's 1, 0, 5, the norm form of the root minus 5 integers. Okay, here's where it gets interesting. We have 3 possibilities if A is 2. B has to be even. So what are the 3 possibilities? Can you write them in to the chat? B can't be bigger than A in absolute value, and A is 2. Yep, -2, 0, or 2. So now we have to see what our possible answers for C are. So C, remember D is -20. -20 has to be B squared minus 4AC. So let's solve this equation. This is, let's see, can you guys do it faster than I can? This is 4, I subtract 4 to that side, -4, divide by -4. In fact, this is a 24, this is a -8, C is 3. Yes, thank you. C is 3. So we have the quadratic form 2, 2, 3. If A is 2 and B is 2 and C is 3. Interesting. Interesting. How about if B is equal to 0? Then -20 is 0 minus 4 times 2 times C. But this is 8, and 20 is not divisible by 8. So C is not an integer. Doesn't work. Karen? Did you want to ask something? Nope. Sheik? Why is A 1 or 2? So A squared is at most 6, and A is a whole number. So the only squares less than 6 are 1 and 4. Chang, you wanted to ask something? Great, Cheek. You guys keep starting to ask something and then you choose not to. Are you confused? Can you say confused or good? Can you write that into the chat? Good. Okay. Good. All right. How about if B is -2? So again, -2 and +2, you're going to have exactly the same equation because it's just about B squared. So we get the form 2, -2, 3. Ah, you can't see what I'm... Oh, no, you can see. Okay, you can see. Okay? So now we have 3 forms to consider. These are 3 forms. And I think these are all 3. But we have to be a little bit careful. So what is the root of the first one? So let's call this... I already called this Q2. Well, let's just write alpha sub the root. 105. So what is the root of this form? -b plus root d root 5i over 2. Does everybody see that? So where is that in the fundamental domain? Here's -1/2, and 1. Root 5i over 2 is up here. In fact, if you use that and 1, that generates exactly that lattice. Everybody see that? How about what's the root of 2, 2, 3? -b plus square root of, it's still the same discriminant, which is, the discriminant is 20. Oh, what did I write? Why did I write root 5? Root 5i, thank you, yes. It's root 20. It's root 20. Root 20, also known as, if I pull out a 4, the square root of 4 is 2, that cancels the 2. This is up here at 5i, that's better. That's better. That generates the full lattice. How about here? Again, I get root 20i over twice a. So this is -1/2. Ah, the real part is -1/2. That means we're on the boundary. The boundary of this is real part is -1/2. So you have to know that we're going to get another one. The 4 cancels here, and I get plus root 5 over 2i. So -1/2 plus root 5 over 2i is over here somewhere. And alpha of 2, what's the other one? -2 3 is going to be the same thing except with a plus 2. So that's a plus a half plus root 5 over 2I. So that's right there. And these two are equivalent. So these two are equivalent. So let's prove a little lemma. If Q, being ABC, has discriminant equal to minus 20, not minus 3, we're up to minus 20 now. If we have discriminant minus 20, then either one of two things happens. Either Q is equivalent to 105, or Q is equivalent to whichever one of these you want to pick. But the class number is now 2. There are two equivalence classes of quadratic forms of discriminant negative 20. And these are these two different points in the upper half plane that have this discriminant. All right, let's prove our final theorem, which hopefully now will be very easy. This is a major theorem of Gauss from when he was like 18 years old in his Disquisitiones Arithmeticae. Let Q be a positive definite. I don't want to start with Q. I want to start with discriminant. Fine. Be a positive definite form of discriminant D negative. Then, at first, why do we have to get one or two or finitely many? It's not even clear that we're always going to get finitely many equivalence classes. Then, there exist finitely many reduced forms of the same discriminant such that Q is equivalent to one of them. Q is equivalent to one of them. I mean, this is a very cumbersome way of saying something much simpler. I'm trying to mimic the previous lemmas we had, i.e., the number of reduced forms is finite. Number of reduced forms of a given discriminant negative discriminant of a given negative discriminant is finite. This is called the finiteness of the class number. A major result in the history of number theory. And now it's a very easy theorem for you guys. Let's prove this theorem. If Q is reduced, if Q has discriminant D, which is B squared minus 4AC, and it's actually negative, the absolute value of D, just to drive home the point that D is negative, and is reduced, absolute value of B is at most, absolute value of A is at most C, then let's look again at this equation and move things around to make it positive. 4AC is equal to B squared plus absolute value of D, just by moving things around, exactly as we've been doing all along. B is at most A, B is at most A, so this is A squared plus D. C is at least A, so this is 4A squared. What we were doing in an ad hoc way is a completely general process. If I subtract A from both sides, 3A squared is at most D. So given D, there are finitely many A's. So A is at most square root, I guess, of D over 3. There are finitely many A's. Number of A's is finite. But B, once the A's are finite, the B's are bounded. Number of B's are finite. And once you have A and B and D, C is determined. A and B and D determine C. So that's it. That's the finiteness of the class number of definite, positive definite binary quadratic forms. It's a major, major theorem in the story of mathematics. Led to, it was the beginnings. I mean, you guys already know about ideals and things like this. They didn't know this in Gauss's day. So it was kind of the first, this decomposition is the first step to understanding spaces of lattices, things about algebraic number theory, and all kinds of amazing stuff. All right, so what have we covered all semester long? Let's just have a whole semester review in the last 3 minutes. Review. We started with Pythagorean Theorem. X squared plus y squared equals z squared. The Pythagoreans and the Babylonians well before them. Pythagorean Theorem. And the integer points. Primitive integer points. Primitive z points are parametrized by u squared minus v squared 2uv and u squared plus v squared. We saw that this also parametrizes rational points, q points on the circle, on the unit circle. If x squared plus y squared equals 1 and x and y are rational, that's equivalent to Pythagorean theorem by clearing denominators. From there, we started thinking about what numbers arise as hypotenuses, which z are hypotenuses, that is represented by u squared plus v squared. So we got into sums of two squares. We figured out how to do that. We spent a bit of time. Theorem, a prime is a sum of two squares if and only if, well, it's equal to 2 or it's 1 mod 4 and not 3 mod 4. And then any multiples of these things and any multiples of squares. So n is a sum of two squares if and only if, for all primes congruent to 3 mod 4, the ord sub p of n is even. If you have a prime that's 3 mod 4 that divides n, it has to divide it with a square. And that all came from understanding unique factorization in the Gaussian integers, because this is expressing n as the norm of a Gaussian integers, and being a unique factorization domain. And we had a process that found a representation, and easy to find representations. Easy to find u and v for p. And hopefully you guys remember that process, Dependra. If p is 1 mod 3, for p's that are 1 mod 4, for those that have a representation, it's easy to find that representation. And hopefully you remember how to do that. This is kind of what we did up to the first midterm. The second midterm was, okay, instead of can we say about something about other norm forms? What about primes equal to u squared minus uv plus v squared, which is the norm form in the Eisenstein integers? And that took us into a discussion of ideals. U squared plus v squared lemma. So what do you mean? What about primes that are 3 mod 4? What I'm saying is n has to have, if it has primes 3 mod 4 dividing it, it has to divide it to an even amount, an even number of times. Yep, okay, good. What about this form? That's in the Eisenstein integers. Same thing. So p is represented, so we had a theorem that primes are represented by this form if and only if, well, the prime 3 is represented, or which is it? 1 mod 3 are represented or 2 mod 3? Do you remember? It had better be 1 mod 3 because the algorithm is to find cubic non-residues. And generalization and general statement in the same way. And the proof was from the Eisenstein integers, and again, an algorithm for finding algorithm. Do you remember, should we review the algorithm for a second? Algorithm to find P, to find, I guess, U and V. You take a random A raised to the P minus 1 over 3. That's why I need P to be 1 mod 3. Is likely to be, well, it's likely to be 1, but it's also, with 2/3 probability, is likely to be a number not equal to 1. And if it's not equal to 1, then this is a number whose cube is 1. Then z cubed is 1 mod P. So z squared plus z plus 1 also divides P. Because z cubed, so this means z cubed minus 1 is 0 mod P. Has P as is 0 mod P. So P divides this. I'm just reviewing this whole story. But this factors in the Eisenstein integers as z minus omega times z minus omega bar. And so you take the GCD in the Eisenstein integers of your prime P and z minus omega, and that will find you U plus V omega, a representation. And finally, the general story is n is represented by a quadratic form. The number is represented by, so equivalent, Q1 equivalent to Q2 implies they represent same numbers. Represent same numbers, which led us to find equivalences. So then we looked at the reduction theory to find the simplest quadratic form, and finally, finiteness of the class number, Gauss's theorem. That's it. That's all I got. Thank you guys very much for sticking around all semester